A glowing ring hangs in the blackness of space, a gateway to another galaxy. That iconic image from science fiction points to a real scientific mystery, the wormhole. These are theoretical tunnels through the fabric of space and time itself. We are about to journey through 30 of the most incredible theories surrounding them, from the solid math of Einstein to the strange realm of quantum physics. By the end, you will understand how these cosmic shortcuts could redefine reality. We will explore if they might be hiding in plain sight as dark matter, and whether the universe itself prevents us from using them to travel through time. What single question about the universe would you ask if you could step through a doorway to anywhere? This idea of a cosmic tunnel did not begin with science fiction. It emerged directly from the mathematics of gravity itself. Albert Einstein and his colleague Rosen were exploring the implications of his theory of general relativity when they stumbled upon a remarkable possibility. Their equations described a bridge linking two distant regions of space-time. Picture the fabric of the universe not as a flat sheet, but as a flexible grid. If you could pinch two distant points on this grid and bring them together, you could create a shortcut, a tunnel with a narrow passageway at its center known as the throat. This was the Einstein-Rosen bridge, a theoretical structure where the immense gravity of a black hole could warp space-time so severely that it connected to another point, perhaps even another universe entirely. The math was sound, but it revealed a profound problem. This bridge was incredibly unstable. The moment it formed, the tremendous gravitational forces at its throat would cause it to snap shut. Imagine a tunnel made of rubber that pinches closed the instant you try to step into it. Not even a single photon of light could travel through it before it collapsed. So while Einstein and Rosen gave us the first legitimate blueprint for a wormhole, they also showed us why we could never use it. This initial theory presented a tantalizing doorway to the stars, only to immediately lock it shut, setting the stage for decades of scientific struggle to find a key. That doorway might have slammed shut, but the human mind refuses to accept a locked door for long. Decades after Einstein and Rosen, a new generation of physicists asked a radical question. What if we could build scaffolding to hold it open? The quest for a traversable wormhole began in earnest, led by visionaries like Kip Thorne. He realized the central challenge was the wormhole's throat, that narrow tunnel where gravity's crushing force acts like a pair of cosmic scissors snipping the connection. To build a stable passage, you would need something to fight that force, something to push back against gravity itself. The theoretical solution is as bizarre as the problem. Exotic matter. This is not just a rare element or a strange new metal. Exotic matter, in this context, would possess a property that seems to defy the very nature of our universe: negative energy density. Think of it as a kind of anti-gravity substance, where normal matter and energy create a gravitational pull that attracts. This exotic matter would generate a gravitational repulsion, a pushing force. Lining the throat of a wormhole with this material would be like propping open a collapsing mine shaft with beams that actively push outward against the walls, countering the immense pressure trying to crush it. The challenge, of course, is monumental. No one has ever found or created a stable amount of this kind of exotic matter. Some theories suggest fleeting glimpses of its effects might be seen in certain quantum experiments, like the Casimir effect, where the empty space between two metal plates somehow exhibits a negative pressure. But harnessing that on a scale large enough to hold open a cosmic tunnel is far beyond our comprehension. It would require the energy of a star or the manipulation of physics on a subatomic scale across a vast region of space. So while the math shows a traversable wormhole is possible, it demands a substance that may not even exist in the quantities we need, presenting a barrier not of imagination but of fundamental reality. This theoretical substance might be the key to holding the door open, but what if that door could also become a gateway to the past or the future? The potential for a wormhole to function as a time machine is one of its most breathtaking implications. The mechanism relies on a strange but proven quirk of our universe, time dilation, a central prediction of Einstein's special relativity. Here is how it could theoretically work. Imagine a wormhole with two mouths, entrance A and entrance B. For a moment, they are synchronized, existing in the same present. Now we take entrance B and send it on a journey. It does not just travel through space, it travels at a significant fraction of the speed of light, a relativistic speed. According to Einstein's theories, time does not pass at the same rate for everyone. For an object moving at such incredible speeds, time slows down. It is like having two identical clocks that are perfectly synchronized. You leave one clock on your desk and you take the other on a trip aboard a near-light-speed spaceship. When the spaceship returns, you compare the clocks. The clock that traveled will have ticked fewer seconds. It will be behind the clock that stayed at home. This is not a mechanical error, it is a fundamental property of reality. Now apply this to our wormhole. Entrance B, the one on the high-speed journey, experiences time more slowly than its stationary twin, entrance A. The connection between them, the tunnel itself, acts as a direct link between these two different rates of time. After the journey, the two mouths are no longer in the same present. If you were to step into the stationary entrance A, you would exit from entrance B into its personal timeline, which could now be in your past. Conversely, stepping into entrance B could send you out of entrance A into what was once your future. The wormhole becomes a bridge not just through space, but through time itself, a permanent connection between two different moments. This bridge through time remains purely theoretical, yet the exotic matter required to build it might be hiding in plain sight within the strange quantum realm. We can actually observe a tiny hint of this negative energy effect in laboratory experiments. It is called the Casimir effect. Picture two perfectly smooth, uncharged metal plates placed incredibly close together in an utter vacuum, a space completely empty of all matter. Classically, nothing should happen. They are just two inert pieces of metal, but the quantum world is never truly empty. At the subatomic scale, what we call a vacuum is a seething, bubbling foam of virtual particles. These are pairs of particles and antiparticles that spontaneously pop into existence from nothing, borrowing energy from the universe for a fleeting moment before annihilating each other and vanishing. Now place those two plates very close together, mere nanometers apart. The gap between them is so small that only certain wavelengths of these virtual particles can fit. Outside the plates, any wavelength can flicker into being. This creates a subtle pressure difference. There are more virtual particles pushing on the outside of the plates than there are between them. The result, the plates are very gently pushed together by the nothingness itself. The energy density in that narrow gap between the plates is actually lower than the energy density of the surrounding space. In a sense, that region has a negative energy density, a microscopic shadow of the exotic matter we would need to prop open a wormhole. This real-world phenomenon provides a tantalizing clue that the universe does permit the kind of negative energy required for stability. It leads to a staggering speculation. If this effect exists on such a tiny scale, could nature be forming its own wormholes? Theorists propose that at the very smallest scales of reality, at the Planck length, which is a millionth of a billionth of a billionth of a billionth of a centimeter, space-time itself may be foaming with activity. Within this quantum foam, unimaginably small wormholes could be constantly forming and evaporating, linking and unlinking points in a chaotic, spontaneous dance. These would not be tunnels for starships. They are transitory bridges between different locations or even different moments, far too small and unstable for anything, even a single electron, to pass through. They are the universe stitching and unstitching its own fabric at the most fundamental level. This vision transforms our cosmos from a smooth, empty stage into a dynamic, bubbling quantum ocean, where the potential for connection exists everywhere if only we could learn to see it. While we grapple with the fleeting wormholes of the quantum foam, another theory proposes a cosmic architecture on an unimaginably grand scale. This idea suggests that wormholes could be forged not from tiny quantum fluctuations, but from the scars of the universe's own violent birth. These scars are known as cosmic strings. Picture the fabric of space-time cooling and settling after the Big Bang. Theorists propose that as it crystallized into the universe we know, one-dimensional flaws might have formed like cracks forming in ice. These are cosmic strings, filaments of pure energy thinner than a single atom but stretching across the entire cosmos. Their density is almost beyond comprehension. A single inch of a cosmic string could weigh more than a mountain range, and the gravitational tension surrounding one would be immense, warping the space around it into a deep, narrow funnel. Now imagine two of these cosmic strings, these ultra-dense threads of primordial energy, moving through the universe on parallel paths. As they pass near each other, their combined gravitational influence would not simply add together. It would twist and contort the fabric of space-time between them into an entirely new shape. The profound warping caused by their mutual attraction could theoretically pinch space-time so severely that a bridge forms, a tunnel linking their two distant locations. This would not be a fragile quantum wormhole. It would be a massive, potentially stable structure, a permanent feature of the cosmic landscape woven from the fundamental flaws of reality itself. The passageway would be held open not by exotic matter, but by the sheer, relentless gravitational pull of the strings themselves, acting as cosmic anchors for a gateway across the stars. This vision transforms wormholes from temporary quantum hiccups into part of the universe's fundamental infrastructure, a network of superhighways left over from creation. The universe loves to hide its greatest secrets behind terrifying masks. Black holes have long been cast as the ultimate cosmic monsters, regions of gravity so intense that nothing, not even light, can escape their clutches. It is a one-way trip into oblivion, ending at a point of infinite density called a singularity. But what if that is not the end of the story? Some theories propose that a black hole is not a final destination but a gateway. The terrifying event horizon, the point of no return, might not be a wall but a doorway, and on the other side could be the throat of a wormhole. This idea is woven into the very fabric of the Einstein-Rosen bridge, the first mathematical model of a wormhole. In that framework, the bridge was not a separate structure, it was what connected two black hole-like points. You would fall through one black hole, traverse the bridge, and emerge from another. This other end, however, presents its own puzzle. If one side is a black hole that only swallows, what is the other side? Theoretically, it could be its opposite, a white hole. A white hole is a hypothetical region of space-time that only expels matter and energy. Nothing can ever enter it. It is a cosmic fountain, spewing out everything that fell into the connected black hole. This creates a breathtaking circuit, a black hole in our universe acting as a drain, connected by a wormhole to a white hole in another universe or another time, acting as a source. This elegant idea even offers a potential solution to one of physics' most vexing problems, the black hole information paradox. According to quantum mechanics, information about what falls into a black hole can never be truly destroyed. But general relativity suggests it is lost forever inside the singularity. The paradox is a direct conflict between our two best theories of reality. If a black hole is actually one end of a wormhole, the information is not destroyed. It is simply transferred, carried safely through the tunnel, and sprayed out the white hole into another realm. This transforms the black hole from a cosmic shredder into a cosmic teleporter, preserving the information of everything it consumes. While we have no evidence for white holes, this possibility reshapes our understanding of the most destructive objects in the universe, suggesting their darkness might conceal a brilliant exit. That elegant cosmic circuit where a black hole drains matter into a white hole fountain is a beautiful idea, but it forces us to confront the nature of this other end. A white hole is the complete theoretical opposite of a black hole. Where a black hole's event horizon is a point of no return, a one-way street into oblivion, a white hole's horizon is a point of no admission. Nothing, absolutely nothing, can ever cross it from the outside. It is a cosmic bouncer that refuses all entry. Matter and energy can only erupt from within, spewing out into the universe. Imagine a black hole as a drain in a cosmic sink pulling everything down. The white hole would be that same drain, but now acting as a geyser, violently shooting everything back up. If these two are connected by a wormhole bridge, it creates a self-contained system. Everything that falls into the black hole is instantly, or perhaps not so instantly, ejected from the white hole. This provides a stunningly clean solution to the information paradox, as the information is not lost, it is merely relocated. The problem is that white holes, while mathematically possible within Einstein's field equations, are considered profoundly unstable. Think of them as a mountain of matter and energy desperately trying to explode outward, but held in check by its own immense gravity. The slightest perturbation, a single speck of dust trying to fall in, could theoretically trigger a catastrophic collapse, converting the entire white hole into a black hole. It would be like balancing a pencil perfectly on its point, a state that is possible in theory but instantly destroyed by the slightest breath of reality. This inherent fragility is why most physicists believe that if white holes ever did form in the early universe, they would have blinked out of existence almost immediately. Yet they remain a captivating part of the puzzle, a necessary mirror to complete the reflection of a traversable wormhole, showing us that the universe's equations often contain hidden symmetries, even if nature chooses not to use them. The universe seems to operate by two conflicting sets of rules. On the grand scale, Einstein's general relativity describes the graceful curvature of spacetime by planets and stars. In the tiny quantum world, particles engage in a bizarre dance, instantly influencing each other across any distance. For decades, these two pillars of physics have refused to speak the same language. But a revolutionary idea is building a bridge between them, and the blueprint is written in wormholes. This is the ER equals EPR conjecture. ER stands for Einstein and Rosen, the very bridge we began with. EPR stands for Einstein, Podolsky, and Rosen, who first identified the strangest phenomenon in quantum physics, entanglement. The conjecture boldly proposes that these two ideas, born from the same brilliant mind but describing different realms, are actually two sides of the same coin. It suggests that when two particles become entangled, their mysterious connection is not some invisible, instantaneous signal. It is a physical structure. They are linked by a microscopic wormhole. Think of two electrons created together so that their spins are linked. If you measure one and find it spinning up, you instantly know the other is spinning down, no matter if it is across the room or across the galaxy. Einstein called this spooky action at a distance, deeply troubled by the implication that information seemed to travel faster than light. But if ER equals EPR is correct, there is no spooky signal. The particles are not communicating, they are simply two ends of the same tiny tunnel. The information does not travel across space, it takes a shortcut through the wormhole's throat. This transforms our understanding of the quantum world. Entanglement is not a ghostly connection, it is the fabric of spacetime itself woven into a subatomic bridge. This single, elegant idea could be the key to a theory of everything, showing that gravity and the quantum world were never truly apart. They were just waiting for us to find the doorway that connects them. The violent chaos of the universe's first moments may have been the ultimate cosmic workshop. In the searing heat and unbelievable density just after the Big Bang, the fabric of reality was not the smooth, stable stage we see today. It was a turbulent, rapidly expanding froth, subject to immense pressures and wild fluctuations in energy. Under these extreme conditions, space-time itself could have been twisted and knotted, much like a pot of boiling water forms intricate bubbles. Some of these knots could have pinched off into stable topological structures, creating natural wormholes. These were not engineered shortcuts, but birthmarks woven into the very fabric of the expanding cosmos. The key to their survival was the period of cosmic inflation, that unimaginably rapid expansion of the universe that happened in a fraction of a second. A tiny, stable wormhole formed in the initial chaos could have been stretched to an enormous size by this inflationary surge. Its two mouths, once impossibly close, were suddenly flung across vast cosmic distances, yet they remained connected by that primordial thread. This leads to a staggering possibility. Scattered throughout the modern universe, from our galactic neighborhood to the farthest voids, there could be ancient wormholes that have survived for over 13 billion years. They would be fossils from the dawn of time, each one a permanent tunnel linking two wildly separate parts of the cosmos. What role could these relics play today? One compelling theory suggests they might be the invisible architects of the universe's largest structures. The immense gravitational pull of a wormhole's throat could have acted as a seed, drawing in ordinary matter to form the first galaxies and galaxy clusters. Even more intriguing is the proposal that these primordial wormholes could solve one of astronomy's greatest mysteries, dark matter. We know dark matter exists because of its gravitational pull on galaxies, but we cannot see it. What if it is not a cloud of exotic particles, but a network of these invisible tunnels, each wormhole with the mass of a small planet or even a star compressed into its narrow throat, would exert a powerful gravitational influence without emitting or reflecting any light. They would flow through the cosmos like ghostly anchors, shaping the rotation of galaxies and the bending of light, all while remaining completely undetectable to our telescopes. This means the missing mass of the universe might not be a form of matter at all, but a hidden architecture of bridges, a cosmic web of connections left over from the very first second of everything. This unseen architecture of wormholes could be the answer to a mystery that has puzzled astronomers for nearly a century. Dark matter is the ghost in the cosmic machine, an invisible substance whose gravity holds galaxies together. We know it is there because stars on the outer edges of galaxies orbit far too quickly to be held by the pull of visible matter alone. Something unseen must be providing the extra gravitational glue. For decades, the leading theory has been that dark matter is made of some kind of exotic, undiscovered particle. But what if we are looking for the wrong thing entirely? What if dark matter is not a particle but a place? The proposal is that a vast population of primordial wormholes, forged in the Big Bang and scattered everywhere, could collectively account for the missing mass. Each wormhole's throat, a point of ultra-dense, warped space-time, would possess significant mass and therefore a powerful gravitational pull. Yet, because it is a tunnel, a feature of geometry rather than a lump of matter, it would not interact with light at all. It would be perfectly dark. These objects would flow through galaxies like invisible anchors, their combined gravity dictating the motion of stars without ever revealing themselves directly. How could we ever hope to find such a ghost? The key is a celestial phenomenon called gravitational microlensing. Imagine a single, primordial wormhole drifting through space in the vast expanse between us and a distant star. As it passes directly in front of the star's line of sight, its intense gravity acts like a lens, bending and focusing the star's light. From our viewpoint, the star would temporarily appear to brighten, then fade, as the wormhole's gravitational lens moves across it. Astronomers already use this technique to search for faint objects like rogue planets or brown dwarfs. A survey looking for these specific, telltale flashes of light could, in theory, reveal a population of these ancient wormholes. The challenge is that the signature would be nearly identical to that of any other massive, compact object. The true test would be in the statistics, finding a number of these lensing events that cannot be explained by known celestial bodies. It is a cosmic hunt for shadows where the prey is not a thing but a tunnel, a doorway whose gravitational footprint might be the very thing holding our galaxy together. That cosmic hunt for shadows leads us to a profound and unsettling question. If wormholes can bridge time itself, why does our history seem so secure, so immune to visitors from the future? The legendary physicist Stephen Hawking pondered this deeply, and his answer was both elegant and defiant. He called it the chronology protection conjecture. Hawking essentially proposed that the universe has a built-in set of laws that act as a paradox police. The fundamental rules of physics, he argued, simply will not allow time travel on a macroscopic scale. The conjecture suggests that any attempt to transform a wormhole into a functional time machine would trigger its own instantaneous destruction. Here is how this cosmic failsafe might work. As you begin to manipulate a wormhole to create a closed time-like curve, a path that circles back onto its own past, the vacuum of space around it would rebel. The empty space we think of as nothing is actually filled with seething quantum fluctuations, virtual particles that flicker in and out of existence. In a stable region of spacetime, these fluctuations average out to zero. But in the twisted geometry of a nascent time machine, this balance is shattered. The particles that appear just before the time loop is completed would be able to travel through the loop and reappear at their own starting point again and again. With each pass, their energy would be amplified, feeding back into the system in an unstoppable runaway chain reaction. The energy would build up exponentially in a fraction of a second, becoming infinite. This incredible surge of raw power would not just destabilize the wormhole, it would vaporize it. The very fabric of the tunnel would be torn apart by the energy of the nothingness it sought to conquer. It is a built-in circuit breaker, a fundamental law that ensures cause always precedes effect. So while the mathematics might permit a path into yesterday, the universe itself seems to slam the door shut, preserving the single, consistent story of reality that we all share. Hawking's cosmic failsafe protects our timeline, but what if some journeys bypass our universe entirely? Wormholes may offer a passage not just through space and time, but out of our cosmic bubble altogether. This idea connects directly to one of the most profound theories in modern cosmology, the multiverse. Picture our entire universe with all its hundreds of billions of galaxies as a single bubble floating in an inconceivably vast cosmic foam. Each of these bubbles is a separate universe, potentially with its own unique set of physical laws. In our bubble, the force of gravity has a specific strength, and the speed of light is a fixed constant. But in the bubble next door, gravity might be 10 times stronger, or light might travel at half the speed. The fundamental forces that hold atoms together could be completely different, making chemistry and even matter itself unrecognizable. A traversable wormhole could theoretically be a tunnel piercing the skin of our bubble and connecting it to another. You would not be traveling to a distant star in our cosmos. You would be stepping into an entirely new reality. The throat of the wormhole would act as a protective corridor, shielding you from the violent, possibly destructive physics of the space between universes. This transforms the wormhole from a mere interstellar shortcut into an inter-universal gateway. The implications are staggering. A civilization that mastered wormhole travel would have access to an infinite cosmic library of realities. They could visit a universe where dinosaurs never went extinct, or one where the conditions for life are utterly alien. They might find realms made of pure energy, or universes so ancient that their stars have all burned out. The journey, however, would be one of unimaginable risk. Stepping out into a universe where the nuclear forces are slightly weaker could cause every atom in your body to instantly fly apart. Or you might find yourself in a reality so dense and heavy that you are crushed into a speck the moment you emerge. The wormhole is the door, but the destination is a roll of the cosmic dice, offering wonders and terrors beyond human comprehension. While the universe seems to guard its timelines, perhaps there is another path around the problem. Physicist Sergei Krasnikov proposed a radically different kind of cosmic shortcut, one built not as a tunnel, but as a highway laid down during the journey itself. This is the Krasnikov tube. Imagine a starship embarking on a long voyage to a distant star. As it travels at near light speed, it does not just move through space, it actively warps the spacetime behind it. Using some hypothetical form of negative energy, much like the exotic matter for wormholes, the ship would permanently modify the fabric of reality along its route. It would create a fixed tube of distorted spacetime connecting its starting point to its destination. The magic of this tube is not in the initial outbound trip, which still takes considerable time, but in the return journey. Inside this pre-established corridor, the local speed of light is effectively much higher. A ship traveling back through the tube could achieve speeds that, to an outside observer, appear faster than light, all without ever breaking the universal speed limit within its own local environment. This solves the agonizing problem of cosmic distances in a completely different way than a wormhole. A wormhole is an instantaneous bridge, a door you step through to be somewhere else immediately. The Krasnikov tube is a pre-built superhighway you use for a swift return trip. It is the difference between a teleporter and a warp drive. Crucially, this method may also avoid the terrifying time travel paradoxes that plague wormhole theories. Because the tube takes time to construct on the initial slow journey, it cannot be used to go back in time and prevent its own creation. The sequence of events remains safely linear, dodging the universe's paradox police. Krasnikov's concept offers a fascinating alternative, suggesting that if we cannot jump through space, we might instead learn to pave it, leaving a trail of modified physics in our wake for a faster way home. A rotating black hole spins the fabric of reality into an entirely new shape. The classic image of a black hole is a simple, deadly point of infinite density, a singularity from which there is no return. But nature is rarely so simple. When a black hole rotates, which almost all of them do, that simple point stretches and twists into a ring. This is the ring singularity, a theoretical loop of ultra-dense material spinning at a significant fraction of the speed of light. The mathematics of this object, described by the Kerr solution, are far more complex and far more intriguing than its static cousin. The ring does not just sit there. Its immense rotation drags the very fabric of spacetime around with it, a phenomenon known as frame dragging, creating a vortex of twisted dimensions around the central ring. This violent whirlpool warps the geometry of space in a way that opens up a breathtaking possibility. The center of the ring might not be a wall but a portal. Theorists propose that if you could somehow navigate the chaotic tides of gravity and radiation surrounding it, and aim precisely for the center of that spinning ring, you would not be crushed into nothingness. You might pass through the ring itself, entering a wormhole that leads to another universe or a distant point in our own. This is not the symmetrical Einstein-Rosen bridge. It is a one-way door, a cosmic whirlpool that could spit you out into a completely new reality. The journey, however, is beyond any human engineering. The tidal forces near the ring singularity would stretch and compress any object in a process whimsically called spaghettification, turning you into a stream of particles long before you reach the threshold. And the exit is just as uncertain. You might emerge into a universe with different physical laws, or be trapped in a region of spacetime with no way back. Yet this theory transforms the most terrifying objects in the cosmos into potential gateways, suggesting that within the heart of a spinning black hole, a doorway waits, hidden behind a veil of unimaginable force. That gold standard model for a traversable wormhole came from a collaboration between science and fiction. When the renowned physicist Kip Thorne was consulted for the movie Contact, he set out to design a wormhole that was not just mathematically possible but potentially usable. Together with his student Michael Morris, they developed the first truly rigorous blueprint for a stable wormhole. The Morris-Thorne wormhole is a specific, elegant solution to Einstein's equations of general relativity. It describes a perfectly spherical and static tunnel, a symmetrical gateway that does not spin or change over time. Picture not just a ring, but a three-dimensional sphere as the entrance, a hole in space that opens into a smooth, curved throat. This throat is not a long, dark passage. It is the shortest possible bridge, a minimal surface where the fabric of space-time is stretched to its limit, connecting two distant regions of the universe. The geometry is mathematically beautiful, a hyperbola of revolution that creates the most efficient shortcut imaginable. But this elegant shape is utterly impossible without the crucial ingredient, exotic matter. Morris and Thorne calculated the exact properties this substance must have. To hold the throat open against the relentless force of gravity, the exotic matter threading the tunnel must exert an immense negative pressure, a repulsive gravitational force. The equations show that this material must violate what is known as the average null energy condition. In simpler terms, this means that for any observer passing through the wormhole, the energy density of this exotic matter must always appear negative. It is not enough for it to be negative on average. It must be negative at every single point along the journey. This is a far more demanding requirement than a simple aggregate of positive and negative energy. It is a continuous thread of anti-gravity woven through the very fabric of the tunnel, actively pushing outward at every location to prevent the throat from pinching shut. This model transforms the wormhole from a vague concept into a precise engineering schematic. It shows us the exact shape of the doorway and the specific properties of the key needed to turn the lock. While we still lack that key, the Morris-Thorne model gives us a target, a clear vision of what a stable gateway through the cosmos would truly require. A naked singularity would be the most exposed secret of the universe. Roger Penrose, one of the great architects of black hole physics, proposed the cosmic censorship hypothesis, a rule that nature herself must follow. It states, in essence, that every gravitational singularity must be clothed, hidden from our view behind the impenetrable curtain of an event horizon. This is not just a suggestion, it is a necessary law to preserve the predictability of physics, to prevent the infinite, chaotic density of a singularity from affecting the outside cosmos. But what if this rule were broken? A naked singularity would be a point of infinite density hanging in plain sight, a raw wound in the fabric of space-time with no event horizon to shield the universe from its absurd physics. The forces near such an object would be indescribable, warping reality in ways that defy all known laws. And it is within this chaos that a possibility emerges. The incredible warping could twist space-time into a bridge. Without an event horizon to block the way, a spacecraft could theoretically approach this point of infinite curvature and, instead of being crushed, be funneled through it. You would not hit a wall, you would be shunted through a gateway, a wormhole born from the universe's most violent and unclothed secret. The journey would be a gamble with reality itself. The instability of a naked singularity means the gateway could collapse the moment you enter, or it could send you tumbling into a completely different region of space-time, or even a different universe altogether. While most physicists believe the cosmic censorship hypothesis holds true and nature forbids such exposed monsters, their theoretical existence reminds us that our universe's rulebook might have pages we have not yet dared to turn. Our universe might be a three-dimensional membrane adrift in a higher dimensional sea. This is the startling proposal of string theory and brain cosmology, models that suggest reality has more than the three spatial dimensions we experience. We live on a brain, a slice of this higher dimensional reality, while all around us extends the bulk, a realm of extra dimensions that are curled up or otherwise inaccessible. In this grander architecture, a wormhole could function in a completely different way. It might not be a tunnel that twists through our own three-dimensional space, but a bridge that simply steps outside of it. Imagine a garden hose stretched across a lawn, representing our universe. An ant, confined to the two-dimensional surface of the hose, must walk the entire curved length to get from one end to the other. But if the ant could access the third dimension, it could take a breathtakingly direct shortcut, climbing off the hose, moving through the air, and landing on the other side in an instant. This is the essence of a higher dimensional wormhole. It bypasses the long, winding roads of our cosmos by traveling through the shortcut of the bulk. The journey would be invisible to anyone watching from within our brain. A ship would seem to vanish from one point and instantly reappear at another, having taken a path that does not exist in our familiar geometry. The energy required to punch through our brain and into the bulk would be astronomical, but the reward would be a form of travel that makes the vast distances between stars seem as trivial as an ant stepping over a tube. This self-creation paradox strikes at the very heart of causality. The blueprint for the wormhole generator arrives from the future, allowing the past civilization to build the very device that will one day send those same plans backwards. Where did the knowledge originally come from? It was not invented, it was simply received, a perfect closed loop with no beginning. This is a bootstrap paradox, an object or idea that literally pulls itself into existence by its own bootstraps, defying the linear chain of cause and effect that governs our everyday reality. It challenges the fundamental principle that everything must have an origin. The information seems to exist outside of time, a ghost in the cosmic machine. Could the universe permit such a thing? Quantum mechanics offers a strange, potential resolution through the concept of probability. In the quantum world, before something is observed, it exists in a haze of all possible states. Perhaps the original blueprint never had a single, definite origin. The moment the past civilization receives the plans, the act of observation collapses a probability wave that had always included the potential for those plans to simply be there. The timeline is not a straight line with a clear starting point, but a self-consistent loop where the cause and the effect are one and the same, forever intertwined. Yet, this is precisely where Stephen Hawking's chronology protection conjecture would likely draw the line. The universe's paradox police would not tolerate such a macroscopic violation of causality. The instant the time-traveling information created a closed causal loop, the vacuum fluctuations would run amok, the energy would skyrocket to infinity, and the wormhole would be obliterated in a flash of cosmic enforcement. The universe seems to insist on a clear story, one where every effect has a cause and nothing, not even the secret of its own creation, can come from nothing. The universe's paradox police may forbid time loops, but a deeper mystery lies at the very heart of the wormhole itself. To truly understand these cosmic shortcuts, we must venture to the narrowest point of the tunnel, the throat where the fabric of reality is stretched to its absolute limit. It is here that our current understanding of physics shatters. General relativity, which so beautifully describes the warping of spacetime by stars and galaxies, meets its end. The gravitational forces at the throat are so infinitely strong that the smooth, geometric picture of spacetime dissolves into a chaotic, fuzzy storm. This is the domain of quantum gravity, a theory that remains the single greatest unsolved problem in modern physics. Without it, any blueprint for a wormhole is fundamentally incomplete, like trying to build a skyscraper with an architect's drawing that turns to blank paper at the foundation. The equations of Einstein simply cannot tell us what happens where gravity becomes quantum. The smooth continuum of spacetime must be replaced by something else, a granular, discrete structure at the tiniest possible scale, the Planck length. Two leading candidates attempt to describe this new reality. Loop quantum gravity proposes that space itself is not continuous, but woven from tiny, finite loops, a fabric of spun threads of gravity. In this view, the wormhole's throat might be a specific, stable weave in this cosmic tapestry, preventing the catastrophic collapse that classical physics predicts. String theory, on the other hand, suggests that the fundamental units of reality are not points but vibrating strings. At the Planck scale, the wormhole's throat could be a dynamic, vibrating string loop, holding the gateway open through its own consistent resonance. The central question both theories grapple with is whether this quantum structure can withstand the titanic forces at play. Can the threads of loop quantum gravity be tied into a knot strong enough to resist being pulled apart? Can the vibrating strings of string theory maintain a harmonious frequency that counters the gravitational roar? Or does quantum mechanics itself introduce a fundamental instability, a fuzziness that guarantees the wormhole will always and inevitably implode? The answer lies in the quantum nature of reality, a realm where certainty is replaced by probability. Until we can peer into that storm and unite the colossal force of gravity with the spooky rules of the quantum world, the ultimate fate of every wormhole will remain a beautiful, untestable dream. The universe may be a hologram, a stunningly realistic projection of a simpler reality. This is the holographic principle, a radical idea emerging from the study of black holes and quantum gravity. It proposes that all the information needed to describe our three-dimensional cosmos, every star, every person, every event, is not stored within the space itself. Instead, it is encoded on a distant, two-dimensional surface that surrounds us, like the data on a Blu-ray disc projecting a full immersion movie. In this breathtaking framework, a wormhole undergoes a profound transformation. It is no longer a physical tunnel through space you could fly a ship through. It becomes something far more abstract and strange, a direct correlation between entangled bits of information written on that remote cosmic boundary. Picture 2 points in our three-dimensional world that are connected by a wormhole. In the holographic description, these two locations are not linked by a geometric bridge. They are linked because the information describing them on the two-dimensional surface is deeply, fundamentally entangled. Traversing this kind of wormhole would not be a journey through a dark passage. It would be a form of quantum teleportation. Your entire physical pattern, all the information that makes you you, would be transferred from one set of entangled data bits to another. From the perspective of the three-dimensional universe, you would vanish from one point and instantly reappear at the other. The wormhole is the manifestation of that invisible information link, a ghostly connection made real. This idea elegantly ties together the physics of black holes, quantum entanglement, and the very fabric of space-time. The ER equals EPR conjecture we explored earlier finds its ultimate expression here, suggesting that every connection in space, every wormhole, is fundamentally a quantum connection. The cosmos we perceive as a vast physical arena might be the emergent result of an immense interconnected web of quantum data, where traveling across the galaxy is just a matter of rewriting the code. Control over the cosmic doorway would become the ultimate political prize. If humanity ever mastered wormhole technology, the first and most explosive question would be one of ownership. Who gets to hold the keys to the universe? This is not merely a scientific challenge. It is a profound geopolitical and ethical dilemma that would reshape our civilization overnight. The nation or corporation that controlled a stable wormhole would command the ultimate strategic choke point, a gateway through which all interstellar travel and trade must flow. They could levy taxes on entire star systems, control the flow of information and resources, and project military power across light years in an instant. The very map of human influence would be redrawn, with these portals becoming the new centers of power, far more valuable than any strip of land or body of water on Earth. The scramble to claim and fortify these gateways could ignite conflicts that make every past war seem like a minor border dispute. We could see the rise of a wormhole hegemony, an empire built not on continents but on control of the cosmic infrastructure itself. This power would unlock two divergent futures. One path leads to a golden age of exploration and unification. Imagine a network of wormholes connecting Earth to 100 habitable worlds. The exchange of knowledge, culture, and resources could propel our species into an era of unprecedented prosperity and cooperation. We could spread life to barren planets, creating new branches of Earth's biosphere across the galaxy. Diseases could be cured with alien biochemistry, and energy shortages could become a forgotten relic of history. In this vision, wormholes become a great unifier, rendering national borders obsolete and fostering a true planetary and then galactic identity. The very act of looking back at our tiny, pale blue dot from a dozen different star systems might finally dissolve the ancient prejudices that have divided us. Yet the other path is far darker, a descent into galactic imperialism. The same wormhole that allows for peaceful expansion also serves as the perfect tool for conquest and exploitation. A technologically advanced Earth could treat new worlds as colonies, stripping them of rare materials and imposing its will upon any nascent life forms. The concept of manifest destiny would be projected onto a cosmic scale. This raises one of the most critical ethical questions we would ever face, the problem of contamination. Sending a single microbe through a wormhole to an alien ecosystem could trigger an ecological apocalypse, wiping out unique forms of life before we even knew they existed. The ethical framework for first contact would need to be rewritten from scratch. Do we have the right to alter another world, even with good intentions? Would we observe from a distance or intervene, playing God with civilizations that may be millions of years ahead of or behind our own? These questions inevitably lead to the concept of wormhole rights. Would access to these cosmic shortcuts be considered a human right, a necessary utility for the free movement of people and ideas? Or would they be the private property of whoever discovered or built them, a patented technology locked behind exorbitant fees? International treaties, a cosmic version of the law of the sea, would be desperately needed to prevent all-out war over these portals. We might see the creation of a unified galactic transit authority to manage traffic and ensure neutral access, but establishing such a body would require a level of global trust and cooperation we have never yet achieved. The wormhole, a marvel of physics, becomes a mirror reflecting our deepest societal flaws and our highest aspirations, challenging us to evolve not just technologically but morally before we step through to the other side. Our universe may not be a one-time event, but a single heartbeat in an endless cosmic cycle. This is the theory of the cyclic universe, a cosmos that expands from a big bang, contracts into a big crunch, and then explodes outward once more in an eternal loop of death and rebirth. In this model, the ultimate fate of everything is not a cold, dark fade, but a fiery return to the primordial seed. Within this grand, cyclical rhythm, wormholes could play a role far more profound than mere shortcuts. They could become the universe's memory. Imagine a wormhole formed in the first moments of our current cycle, a stable tunnel woven into the fabric of space-time. As the universe expands, its two mouths are flung to opposite ends of reality. Then, billions of years from now, when gravity finally halts the expansion and everything begins to collapse, this wormhole would remain. While stars are torn apart and galaxies merge into a searing plasma, the wormhole persists, a topological knot too tight for the collapse to undo. It survives the big crunch, the point of infinite density where our universe ends. And when the next universe bursts into existence from a new Big Bang, the wormhole is still there, re-inflating along with the new space-time, its connection intact. This transforms it from a bridge across space into a bridge across time, linking one cosmic incarnation to the next. It becomes a relic, a cosmic archive carrying information from a dead universe into its newborn successor. This could solve one of the most puzzling mysteries in all of physics, the problem of fine-tuning. Why do the fundamental constants of nature, the strength of gravity, the mass of an electron, seem so perfectly calibrated to allow for the existence of stars, planets, and life? If these numbers were even slightly different, reality as we know it would be impossible. In a single, random universe, this perfection seems like an unbelievable coincidence. But in a cyclic universe connected by wormholes, it is no coincidence at all. The information threading through these ancient tunnels could subtly influence the physics of the new cycle, nudging the fundamental constants toward the same values that allowed complex structures to form before. The laws of physics would not be random with each new bang. They would be inherited, passed down like a cosmic genetic code through the umbilical cord of a wormhole. Our universe's seemingly perfect design might not be a miracle, but simply a legacy, an echo from a cosmos that lived and died long before our own first star ignited. The silence of the cosmos is one of its greatest mysteries. We gaze at a sky filled with billions of stars, each one a potential sun for another Earth, and we hear nothing. The Italian physicist Enrico Fermi captured this paradox perfectly with a simple, devastating question. Where is everybody? If the universe is so vast and so old, surely other intelligent life should have arisen, evolved, and spread across the galaxy by now. Their ships or their signals should be everywhere, yet we see no signs of construction, hear no whispers of conversation. The stars are quiet. One compelling answer might be hidden in the nature of the journey itself. We assume an advanced civilization would expand slowly, sending generation ships on millennia-long voyages between the stars, leaving a trail of evidence we could spot with our telescopes. But what if they skipped that step entirely? A species that masters traversable wormholes would have no need for slow, visible starships. Their entire civilization could be built around a network of cosmic shortcuts. Imagine a galactic subway system with stations orbiting quiet stars, all connected by instantaneous tunnels. They would not travel through the space we see, they would bypass it completely. A trade ship would not fly from Earth to Proxima Centauri. It would enter a local wormhole here and exit from another one there, without ever crossing the 4.2 light-years in between. To our eyes, trained to look for moving lights or radio broadcasts from the void, this civilization would be functionally invisible. Their bustling interplanetary commerce, their cultural exchanges, even their wars, would all occur within a hidden layer of reality, a secret web draped over the visible cosmos. The space between stars would appear empty not because it is, but because all the traffic is taking the underground toll road. This solves the Fermi paradox not by saying aliens do not exist, but by suggesting their infrastructure is written in a language of physics we are only just beginning to learn how to read. Our very presence as thinking beings might be the very reason wormholes remain locked away in theory. This idea connects to the anthropic principle, a philosophical razor that cuts to the heart of cosmic fine-tuning. It suggests that the universe we observe must have the properties it does because if it were any different, we would not be here to observe it. The fundamental constants, the strength of gravity, the charge of an electron, all seem perfectly calibrated to allow for the formation of stars, planets, and ultimately, life. Now apply this logic to wormholes. What if the formation of stable, traversable wormholes was a simple, common process? The cosmos would be utterly unrecognizable. Space-time would be crisscrossed with shortcuts, a tangled web of bridges used by any civilization with the basic knowledge to open a door. The past would be a tourist destination, the future a place you could visit on a whim. History would be a chaotic mess of interventions and paradoxes, with time travelers potentially altering the very events that led to their own existence. In such a radically unstable universe, the long, quiet, uninterrupted cosmic epochs necessary for galaxies to form, for stars to forge heavy elements and for life to slowly evolve on a sheltered planet would be impossible. The background chaos would be too great. The fact that we exist in a seemingly orderly and predictable cosmos, one where we can trace the history of the universe back over 13 billion years without finding a single definitive time traveler in the fossil record, is telling. It implies that the laws of physics as we know them naturally include mechanisms like Hawking's chronology protection that actively suppress these phenomena on a large scale. Our existence as observers, quietly contemplating the stars from a stable planet in a non-chaotic region of space-time, might be the strongest indirect evidence that macroscopic wormholes cannot form. The universe is not built for shortcuts, it is built for the slow, patient unfolding that made our own lives possible. The chaotic quantum foam and the cosmic strings of the early universe are realms far beyond our direct observation. Yet we might be able to study their secrets in a laboratory tank of fluid. This is the incredible promise of acoustic wormholes, a theory that brings the cosmos down to Earth. Physicists create a remarkable setup using a superfluid, a liquid that flows with absolutely no friction. By forcing this fluid to move faster than the speed of sound within the liquid itself, they create an artificial boundary known as an acoustic horizon. Just as nothing, not even light, can escape a black hole's event horizon, sound waves within this fluid cannot cross the acoustic horizon from the inside. They are trapped, perfectly mimicking the one-way nature of a gravitational point of no return. The real magic happens when these fluid flows are engineered with exquisite precision. By manipulating the flow, researchers can create not just one, but two of these acoustic horizons, facing each other and connected by a specific geometric path through the fluid. This entire structure becomes a direct analog for a wormhole. The flowing fluid represents the fabric of spacetime itself, and the trapped sound waves within it act like light particles or photons trying to traverse the cosmic tunnel. This gives scientists an unprecedented testbed. They can probe questions that are otherwise untouchable, like how quantum fields behave when stretched and squeezed in the warped geometry of a wormhole's throat. What happens to the quantum vacuum fluctuations, the virtual particles, when they encounter these artificial horizons? In the safety of the lab, they can watch the analog of Hawking radiation being generated, seeing how the nothingness itself can create real particles. These experiments do not create real gravity or allow for travel, but they provide a living simulation, a playable model of the universe's most extreme physics, offering clues about the true nature of spacetime by listening to the whispers in a fluid. The intricate dance of quantum entanglement might be the key to simulating the universe's deepest secrets. While we cannot build a wormhole in a lab, we may be able to grow one inside a quantum computer. This radical idea hinges on a profound connection, the ER=EPR conjecture, suggesting that the mysterious link between entangled particles is itself a microscopic wormhole. A quantum computer, with its qubits existing in multiple states at once, is a perfect playground to test this. The complex web of correlations between its qubits can be programmed to mathematically mirror the chaotic quantum information dynamics theorized to occur inside a wormhole's throat. In essence, scientists are not creating a physical tunnel, but they are recreating its information processing heart. This is not just a thought experiment. In recent landmark experiments, teams have used a simple quantum processor to simulate a holographic wormhole. They carefully arranged the entanglement of their qubits to model a specific, simplified version of a spacetime tunnel predicted by string theory. By sending a signal through this simulated quantum system, they were able to observe how information traveled, watching it pass through the analog of the wormhole and emerge on the other side, scrambled but intact, just as the physics demanded. This was not a video rendering, it was a functional model of a cosmic gateway operating on the principles of quantum mechanics. These simulations offer us our first tangible laboratory for testing the wildest ideas about quantum gravity. We can now probe questions that were once purely philosophical. What happens to information when it crosses the event horizon of a simulated black hole connected to a white hole? Can we observe the universe's paradox police in action, watching as the simulation prevents a time travel paradox from forming? Each run of the quantum program is a miniature experiment in cosmology, providing data that could finally bridge the chasm between Einstein's graceful spacetime and the spooky rules of the quantum world. The path to a real wormhole may not be paved with exotic matter, but with perfectly entangled qubits running a cosmic code that we are only just beginning to decipher. Physics itself may have built an insurmountable wall around the wormhole. For all the elegant blueprints and hopeful theories, a series of mathematical proofs known as no-go theorems stand as grim sentinels, declaring the entire endeavor impossible. These are not just technical difficulties, they are fundamental statements about how our universe operates, suggesting that the laws of physics are hardwired to prevent such shortcuts. The core of the problem lies in the exotic matter we have always relied upon to prop the door open. To create the negative pressure, the anti-gravity effect needed to keep the wormhole throat from collapsing, this exotic substance must violate what physicists call the average null energy condition, or ANEC. In plain terms, this is a cosmic rulebook that states that energy, on average, must always be positive. Gravity must always attract. It cannot, on a fundamental level, repel. The exotic matter required for a traversable wormhole shatters this rule. It demands a substance that consistently and reliably exhibits negative energy density along the entire path of the tunnel. Imagine needing a type of glue that actively pushes the pieces apart instead of holding them together at every single point of contact. The no-go theorems mathematically demonstrate that any form of matter or energy that obeys the well-tested laws of quantum physics will always, on average, satisfy the ANEC. It will always produce attractive gravity. This means the exotic matter we need is not just rare or hard to make, it is fundamentally forbidden by the universe's own operating system. The very material required to build our cosmic doorway is, according to these proofs, an impossibility. Yet the human spirit of inquiry refuses to surrender so easily. Physicists are actively hunting for loopholes, for subtle cracks in the mathematical armor of these no-go theorems. Perhaps under conditions of extreme curvature, like the warped spacetime near a wormhole throat, the averaging condition breaks down. Maybe quantum effects we have not yet discovered could provide a temporary, localized exemption from this universal rule. Some explore the possibility of dynamic wormholes that exist for only a fleeting moment, too quick for the universe to enforce its energy laws. But these are desperate gambits against a formidable mathematical consensus. The no-go theorems present a sobering reality check, a reminder that the universe may not be an engineer's playground, but a realm with immutable rules that even our most ambitious dreams cannot bend. This quantum foam is the universe's most fundamental texture. At the tiniest conceivable scale, the Planck length, the smooth stage of spacetime dissolves into a seething, chaotic ocean. Here, the concepts of here and there lose all meaning. The void itself is a turbulent froth where unimaginably small bubbles of distorted spacetime constantly form and vanish. These are not empty bubbles. Each one is a microscopic fluctuation in gravity's fabric, a transient warp that can manifest as a virtual black hole or a fleeting wormhole. In this realm, a wormhole is not a rare cosmic engineering project. It is as common as a bubble in a boiling pot, a basic, ephemeral ingredient of reality itself. What we perceive as the empty, continuous space between stars is an illusion, a calm average over this underlying storm. It is the difference between looking at a sheet of paper, which seems perfectly smooth, and viewing it under an ultra-powerful microscope to see the tangled, fibrous pulp from which it is made. Our entire cosmos, with its galaxies and nebulae, rests upon this dynamic, perforated substrate. These wormholes are far too small for anything to traverse, lasting for only a minuscule fraction of a second before the universe's natural energy laws reassert control and they pop out of existence. Yet their constant presence suggests that the potential for connection is woven into the very threads of the cosmos, a hidden architecture of shortcuts humming with quantum potential just beneath the veil of perception. So the information that falls into a black hole might not be lost after all, but merely transferred, preserving the sacred rule of quantum mechanics. This brings us to one of the most elegant rescue missions in all of physics, where the wormhole is the hero. The black hole information paradox asks a deceptively simple question. When something, say a book filled with information, falls past a black hole's event horizon, what ultimately happens to that information? According to Einstein's general relativity, it is irretrievably lost, crushed into the singularity. But quantum mechanics insists that information can never be truly destroyed. It can be scrambled, but it must be preserved in some form. Stephen Hawking's own work showed that black holes slowly evaporate over eons, emitting a faint glow of what we now call Hawking radiation. The paradox is that this radiation appears to be completely random, containing no trace of the information about what fell in. It is as if you burned a library of unique books and all that remained was a pile of identical, featureless ashes. This is a fundamental crisis, a direct conflict between our two best descriptions of reality. The wormhole offers a breathtaking escape route. The solution hinges on the profound connection between entanglement and spacetime, the ER equals EPR idea. When a pair of particles is created just outside the event horizon, one falls in while the other escapes as part of Hawking radiation. They are entangled. According to the conjecture, that entanglement is not a ghostly link, it is a physical structure, a microscopic Einstein-Rosen bridge. This means the information from the book that fell into the black hole is not trapped inside. It is not even in one place. It is threaded through this vast, complex network of tiny wormholes that connect the interior of the black hole to the outgoing Hawking radiation. The information is meticulously encoded in the correlations between all the escaping radiation particles, a cosmic tapestry woven with wormhole threads. From the outside, it looks like random noise, but if you could collect every last photon of Hawking radiation and decode the intricate web of connections, you could, in principle, reconstruct the entire book. There is an even more radical version of this idea. Perhaps the information does not even stay in our universe. The immense gravitational collapse of a black hole could cause a wormhole to pinch off from our spacetime entirely, forming a separate, infant universe. The information from everything that ever fell into the black hole becomes the initial conditions for this new cosmos, a baby universe whose fundamental laws are born from the data of our own. In this stunning vision, black holes are not tombs, they are cosmic nurseries. Every black hole in our sky could be the Big Bang for another reality, with wormholes serving as the umbilical cords, ensuring that no information is ever lost, only reborn. Our final theory takes us to the very edge of physics and philosophy. If traversable wormholes are possible, they force us to confront the true nature of time itself. The ability to travel to the past implies that the past is still there, a place you can actually visit. This leads to a profound model of reality known as the block universe. In this view, the cosmos is not a series of fleeting moments. It is a single, static, four-dimensional structure, a vast block where the past, present, and future all exist simultaneously, laid out with the same permanence as points on a map. Your birth, your life, and your eventual death are all equally real, fixed within this grand cosmic sculpture. We only perceive the flow of time because our consciousness moves along a single track through this block, like a scanner reading a line of text, unable to see the whole page at once. In such a universe, a wormhole is not a machine that changes time. It is simply a shortcut, a geometric fold that connects two distant points within this static structure. Stepping through one is no more magical than taking a tunnel through a mountain instead of going over it. You are not rewriting history, you are just taking a different route through a landscape where every event is already written. This directly challenges our deepest intuition that the past is gone and the future is not yet real. It suggests that free will might be an illusion, a story we tell ourselves as we travel along a predetermined path. The wormhole, then, becomes more than a tool. It is a keyhole through which we glimpse a universe that is complete and entire, a frozen sea of space-time where our journey was never a river flowing, but a path waiting to be walked. We have traveled from the solid ground of Einstein's equations to the strange shores of quantum foam and alternate realities. These 30 theories paint a universe far richer and more interconnected than we ever dreamed, a cosmos stitched together with potential doorways. While a traversable wormhole remains a beautiful dream, the relentless pursuit of this idea has permanently reshaped our understanding of reality itself. It forced us to bridge the colossal force of gravity with the spooky rules of the quantum world, leading to profound insights like the holographic principle and the nature of black hole information. This journey proves that sometimes the destination matters less than the path. By chasing the science fiction fantasy of a cosmic shortcut, we have unlocked deeper truths about the universe's actual operating system. The greatest discoveries are still ahead, hidden in the next question, the next equation, the next gaze at the stars. We would love to hear which of these theories captured your imagination the most. Was it the cosmic strings weaving primordial bridges, or the quantum entanglement linking everything? Or perhaps your favorite depiction comes from a sci-fi movie that dared to visualize the journey? Share your thoughts in the comments below and keep